Thanks. So I will essentially just start with a very brief recap of what we did yesterday. So we discussed 5D gauge series, Coulomb branches, and in fact, got to the point where we characterized them in terms of these representation graphs, where each weight got assigned a sign. And then the claim was that that captures all the different Coulomb branch phases and also how they glue together, how we can do sign changes and go from one to the other in a consistent fashion. And the last thing I discussed was basically gave you sort of a homework, which is consider just the simplest gauge theory, so SU2, and take NF equals to 8 flavors. And we saw that that's nothing we discussed, that actually is the theory that's the KK or the marginal theory that UV completes to the E string. And I think you heard from Shlomo today about the E string, at least that's what he told me he would do. So you know more about the E string today than you knew yesterday at the end of the lecture. So this theory is a gauge theory. What is the set of Coulomb branch phases for this theory? And so the key ingredients here, of course, is that we have a gauge theory. So you have the gauge group SU2, but then the classical flavor symmetry for NF flavors is SO2NF, right? Because we should really think of this as SP1. And then for NF equals 8, so we have a SO16. And the hypermultiplied matter transforms into 2,16 representations of this SU2 times SO16. And what I gave you at the end was basically just this representation graph for this particular representation, this bifundamental representation, and how the roots act. So this is the root of the SU2, and these are the roots of the SO16, and the weights, just to remind you. So why is it not moving? Okay, here we go. The weights are for the LIJs in each of these boxes are a gauge weight plus a flavor weight. And so for the SU2, we have the roots given in terms of the fundamental weights as L1 minus L2, and for the SO16, again, Li minus Li plus 1, and then alpha 8 is L7 plus L8. So that's just what you would write down just from a representation theoretic point of view, but now the key question was, what actually is the set of Coulomb branch phases? So what are consistent sign assignments that are compatible with that? So basically the extended Coulomb branch phases, right? Now we also include these flavor symmetries, right? We think of them as weakly gauged symmetries, flavor symmetries. So SO16 here really is weakly gauged, and we can of course take that gauge coupling to 0 at the end. The extended Coulomb branch phases are consistent sign assignments to these weights that are consistent upon adding positive roots. And one thing we saw, for example, for the fundamental of SUN is that if we have a plus sign, that always propagates to the left, and the minus sign propagates to the right. And if you looked at this problem, and I'm not going to discuss this in further detail, you'll get these are the consistent phases for this problem. So let me explain to you here, just to be a bit more shorthand. The plus sign assignments are blue, and the minus sign assignments are yellow. And this is just, each one of these is a coloring or a sign assignment to this representation graph, okay? So that's just how we want to think about this particular setup. And now for this particular phase here, we start with all blue, and so all pluses in the top and all minus in the bottom. And now we can ask, how can we change the sign assignment consistent with, we still have sort of closure under adding positive roots. And indeed, the only option we have is in fact changing this sign, which actually also accounts for changing that sign. So this is these two here. And so we can continue this. And if you've looked at this problem, you'll find there's a sort of a tree structure emerging. And then at the end, here, there are two choices that you can make. And basically what this corresponds to is, so, right, all of these are phases, it's extended Coulomb branch phases for SU2 with 8 flavors. But we can really think of them also in a way, and that we explained it at the end, with a question about that, as also in a way decoupling fundamental matter as we keep sort of descending down this tree. So in fact, this path here, you can think of it as a Coulomb branch phase for this theory as you do with 8 flavors, but then you can also think of it as an allowed way of decoupling fundamental matter by basically taking that sign change and then decoupling one hypermultiplet. And that reduces the flavor symmetry, effective flavor symmetry, the roots that now actually act between the various representations, right? It's just a subset of roots that act here. So you're actually just getting an SO14 in that case. Right, so each phase, you can also, and we'll discuss this in more general terms once we get to the geometry, why this is really decoupling. This is sort of a comment here. I can also think of these as decoupling hypermultiplets. And so then this tree of theories is really sort of a tree of SU2 with NF flavors, and NF ranges from 8 to 7 to 0, and the branching here is basically that you have for 0 flavors, whoops, okay, so NF equal to 0, you have 2 choices, SU2 0 and SU2 pi. And that's where this branching actually, this is captured in this branching. Okay, so that's essentially just something I wanted to discuss at the end of the first lecture, and that's I hope you looked at it, or if you haven't, this is now sort of the answer to this question I asked: what are the Coulomb branch phases for this very simple theory? Now, this is so far just, just IR gauge theory physics. And so these theories are in fact these so-called rank 1 theories, are called the Seibrecht theories. And you wouldn't attach the name Seibrecht to this kind of theories if they hadn't gotten some more interesting properties. And in fact, indeed, the conjecture, the claim is that as we go to G goes to infinity, we go to the UV, in fact, these theories become interacting fixed points. So these are non-trivial SCFTs. And in fact, one of the characteristics of these is that they have a flavor symmetry in the UV that's actually given by E and F plus 1. So it's not what we see from the gauge theory, which is always this SO2 and F times, in fact, the U1 topological, right? So there's always this conserved topological current that we also discussed yesterday, but they combine and enhance this exceptional group, E and F plus 1. So for example, for NF equal to 7, you get an E8 flavor symmetry, and then you get E6, E7, E6, and so on. So how do we actually see that? And that's where we need sort of a framework to interpolate between these IR descriptions, the Coulomb branch physics, and actually going to the strong coupling. And that's what's taking us to the next step, which is understanding how to do some more geometry, because clearly just using this Coulomb branch approach won't tell us anything about the G goes to infinity limit. Okay, so this brings us to lecture 2, right? So geometric approach to study the G goes to infinity limit, right? So are there any actually questions about what I talked about yesterday or what I just briefly summarized? No? Okay. So at some point, if I don't hear from you, just to make sure someone is there, I will ask a question back to you, and like yesterday. Okay, so why is this geometric framework useful? So we did this, what we consider M theory. We want to get a 5D theory, so we need a 6-dimensional compactification space. We want n=1 supersymmetry, so in fact we need to have some more refined structure on the space. We put M theory on, so let's start with a very sort of vanilla description of it, and I'll refine it as we go on. So it's a non-compact Calabi-Yau threefold X. And in fact, so what this framework, the advantage is, we'll see this models both the Coulomb branch phase or the extended Coulomb branch phases, but also interpolates to G goes to infinity. Okay, so that's the key. Yeah, so this is sort of, it tells us how to connect it to this nice gauge theory story that we just learned in lecture 1, but it also gives us access to that. So today I'll need to talk a little bit more about these geometries, and I actually decided to perhaps use a framework that you might be more familiar with, namely some toric models, and then I'll ramp it up and show you some more advanced methods, how to study actually the most general 5D theory that we know, using some techniques that are slightly more general than just toric models. So using simply sort of algebraic geometry of certain singular Calabi-Yaus. Okay, so why do we need to consider these types of geometries? Well, I said so X is a Calabi-Yau threefold. And so the key for that is, of course, that we want 5D n=1 supersymmetry. We're actually not interested in coupling this to gravity, so we're totally happy to take this to be non-compact, as we're only interested focus, so ignore gravity effects. Right, so you could couple these theories to gravity, then you would have to ask yourself how you compactify these, but we're only interested in gauge theoretic aspects. And then finally, in fact, what we'll need is not just some nice, smooth, non-compact Calabi-Yau geometries, but in fact, we need X has to have what's called a canonical singularity. And so essentially, the way you should think about these geometries is that the CFT points are some singular geometries. There are no compact cycles and there are no scales. So that's basically where the conformal field theory lives. And then as you introduce cycles, either by blowing up cycles or by deforming, so resolving or deforming, you go into the Coulomb branch moduli space or the Higgs branch moduli space. So the singularity is captured, so is capturing the CFT point. So that's going to be the interesting part. Now, what is a canonical singularity? So for any, so X is some algebraic threefold. So in algebraic geometry, you would then associate to that its canonical class. So if you are more differential geometric person, think of it as like C1 for this space. So for Calabi-Yau, C1 would be trivial. So this canonical class essentially, right? So for Calabi-Yaus is trivial, and if you have a singular space, you can ask, can I resolve the space? So can I pop in sort of cycles, compact divisors, so surfaces. So surface meaning real 4-dimensional, complex 2-dimensional. So can I insert them in such a way that I retain the triviality of this canonical class? So a canonical singularity, oops. is such that there exists some map. Is a resolution of the singularity. Right, so think if you know the conifold, that's actually a particularly special case, but think of the conifold, you can find a small resolution and remove the singularity. And you want from this that, in fact, you want a resolution of the singularity so x tilde is smooth. And now such that this kx tilde is just a pullback of kx. And then possibly the sum of AI, EI, I'll explain what these are in a moment, with the AI greater or equal to 0. Now, if we have a Calabi-Yau singularity to start with, kx would be trivial. This is basically kx is just trivial. And then you wonder, okay, so what are these guys over here? These EI, AI, EI. So these EIs are exceptional divisors. So exceptional divisors just means a divisor, right, is real 4 cycles, or complex 2 cycles. And exceptional is just that they arise as you blow up certain loci in your geometry. And as you blow up, you can actually change the canonical class by positive multiples of these exceptional divisors. So, and canonical means that these AIs really have to be greater or equal to 0. Now, what we really would like to have is, so in fact, we will focus in all these lectures on the case where the AI are actually strictly 0. So as you do, you have a singular space, and then you blow up and you introduce more exceptional divisors, the canonical class actually doesn't change. So that's basically what we would like to do. And the case with the AI bigger than 0 is a special case, which are so-called terminal singularities. And the physics of those we're still exploring. So I want to focus on the case when we just have, so the canonical class retains its triviality as we blow up. So we'll focus on AI equals to 0, and this actually means that pi is then called what's referred to as a Crepant resolution. Right, so that when this holds, and in our case, both of these are trivial. And the claim or the conjecture is, so why is this relevant? I have not told you, we've done Coulomb branch physics, and now I'm telling you there's all this algebraic geometry stuff. Why is this relevant? Also, the claim is basically the resolutions of a canonical singularity are sort of in correspondence, and one correspondence with the extended Coulomb branch phases of an SCFT. Or the SCFT corresponds to the singular geometry. Right, so the origin of the Coulomb branch, where the SCFT sits, is the singular geometry. So that actually tells us already that there can't be just one resolution, right? If this is true, we know there are many different Coulomb branch chambers, and that structure needs to be modeled in the geometry. And indeed, this is something that we'll see very shortly. So in fact, generically X tilde is not unique. Right, so given we have some singular X, we'll have many ways of sort of X tilde 1, X tilde 2, X tilde n, and they will also form, in fact, a very similar structure like what we've seen in the Coulomb branch. And one important thing is to understand exactly how the Coulomb branch structure that we've seen is modeled in the geometry, and then to take that and interpolate it to the SCFT point. And that gives you a characterization of the SCFT. So indeed, so different resolutions of singularity of X are related by geometric transitions so the simplest thing that you can think of, for example, like the flop transitions, as in the conifold. Okay, and what we will develop is basically how this exactly matches with the Coulomb branch phases. We'll have to be a bit careful about how we distinguish various cycles in these resolutions. So actually, let me just introduce a little bit of notation. So the complex, so holomorphic cycles in some resolution X tilde, we'll have 4 cycles. So these are the divisors in the threefold, and they can either be compact, for example, P2, or non-compact, like a P1 fibrate over complex line. So let's write this down. And they play a very different role in what we'll be doing next. The compact cycles I will always denote by SI, and the non-compact ones by D alpha. And in fact, if I wrap various M-theory degrees of freedom on them, they give rise to very different objects. So for example, if I wrap on the compact ones and 5 branes, I get strings, for example. The 2 cycles, so these are the complex curves. Again, they can be compact or non-compact. And the compact curves are always going to be denoted by CI. And when we wrap M2 branes, on them we get BPS particles in 5 dimensions. Okay, so this is just to set a little bit of notation and the following. So what we would like to do is now map out what exactly is the structure that is now modeling the Coulomb branch phases. And in fact, those are given by what's called the relative Kähler cone. So the extended Coulomb branch phases are modeled by the relative Kähler cone. So what is the relative Kähler cone? This is basically, I will first define this and then I'll explain what it really corresponds to. So I have X as the singular space, X tilde is a resolution, right? So this is a Cartman resolution. And these are essentially all the divisors. So do you hear this noise in the background?
Yes, there is some noise.
Yeah, right. 1 second. Let me, I should
Okay.
Give me a second. Okay, that should have stopped now. So these are exactly compact divisors. We can think of them as compact divisors, or actually dually Kähler form, 1-1 forms, such that if I take the intersection of these with curves, that's always positive. And in fact, here C are curves that collapse to zero volume in X. So the blow-up introduces divisors, curves, and we'll discuss examples in a moment. And the key is that they're curves that collapse to zero volume. And here we're not interested in curves that just stay at finite volume, but we're only interested in the curves that collapse and then take intersections with these. And we want these to be positive. That's why it's the relative Kähler cone. And this is what, in fact, will be playing the role of the Coulomb branch phases that we're discussing. So essentially, one thing to notice, if you have sort of one of these X tilde, there are various things that can happen as you go to a singular limit. So in fact, you can have various collapsing limits. I promise I'll make an example very shortly, because I realize this is quite abstract, but I will make very concrete examples in a moment. So various collapsing limits, so we can collapse curves, can collapse to points. We can have divisors collapse to curves, or we can have divisors collapse to points. And all of these things, so these are just geometric facts. If you have one of these X tilde resolved, and you're going now to particular points in their moduli, in their Kähler moduli, relative Kähler moduli space, they can be curves that collapse to points, like in the conifold. There can be divisors that, right, you have, for example, a divisor that's a vibration P1 over P1, say, and that can collapse to a P1, and then the divisor can also shrink to zero volume, like a P2 that's collapsed to zero volume. And all of these different things play a role in what we'll see, and I'll sort of give you a very quick preview of what it is. So this here curves collapse, this will correspond to basically BPS states from M2 branes becoming massless. When a divisor collapses to a curve, this will correspond to M2, so basically W bosons become massless. And I'll explain this in a moment, why these are W bosons. If a divisor collapses to a point, this is a strong coupling point. So that's sort of how these geometric things actually tie into this. But of course, right, there's no way for you to understand yet, because I haven't told you yet what the dictionary is, why these assignments of the physics to these geometric transitions actually make sense. And so that's why now I need to actually talk about what the dictionary actually is between the geometry. So I give you sort of a really rudimentary picture of what these geometries, what kind of things happen in such singular geometries once you resolve them, and in the M-theory compactification. So let me do that, and then we can see whether this particular thing becomes clearer. So, right, dictionary. So M-theory on Calabi 3 and 5D n equals 1. So we have, as we said, in M, so actually before we do this, of course, in M theory, we have a metric. It's just 11-dimensional supergravity, and we have the C3 form. There are various couplings for these. And the first thing is we would like to know what is the spectrum as we reduce this to 5 dimensions. So the main thing to focus on first is C3 and how we can actually decompose C3 along various cycles in the Calabi-Yau geometry. So we said we had compact cycles. So these are the divisors, S. And in fact, we can think of divisors, right? They're basically dual to line bundles. So they're dual to the 1-1 forms. So let's call them omega I. So we can take 1-1 forms and now decompose C3 along those 1-1 forms, just in cohomology. So C3 has a decomposition, say AI, omega I, which omega I, 1-1. So I suggestively put R here because, in fact, right, this here will give us now in 5D exactly R U1 gauge potentials. So from each divisor and compact divisor, so actually the key here is compact, right? They don't want to think about compact support and things like this. This really should be a compact divisor, dual to one compact support, one form. I expand the C3 and I get these R1 gauge potentials. So in fact, the first thing that we can note here is that the number of compact divisors is the rank, is R, of our theory in 5D. So this gives us basically a U1 gauge theory. And that smells very much like, Coulomb branch. So how would we get a non-abelian gauge symmetry? So this can arise only if we now have further degenerations of these compact surfaces. If they, for example, have a structure that I can collapse one of these to actually a singularity, and then additional massless degrees of freedom, which come from M2 branes, become light. And that's what I was talking about earlier here, that if we have compact divisors that collapse to curves, and actually curves of singularities, then that becomes the M2 branes wrapped on these collapsed curves, and the fiber of these divisors are the doubly bosons. So in fact, the non-abelian gauge symmetry arises from M2 branes on P1, so rational curve fibers that can collapse within a compact divisor. So what these kinds of divisors are called are sort of ruled surfaces. So there's a ruling, and all this means is there's a P1 that fibers the compact divisor over another curve sigma. So sigma is some curve, can be of higher genus, and this is P1, so that's just an S2. And as I now, if there is such a vibration structure, and in fact, if I call this F for fiber, then S dot F, the intersection of these, if this is -2 and F squared is 0, then this vibration, I can collapse it, and this ruling will then M2 branes on a collapsed F will become light. So these are exactly the W bosons of the theory. And if you now have, so this was just for one particular compact surface, if you now have multiple of them that intersect in a pattern that is, say, for example, ADE Dinkin diagram, then that actually gives you a full set of A or D or E type singularities over curve sigma. And so we get an ADE worth of P1s, and as we collapse these, the M2 branes become light and then furnish the W bosons for the ADE Lie algebra. So if exists a collection of surfaces, compact surfaces, that intersect as and the Cij is the Cartan matrix of some Lie algebra G, then, and these have these rulings, then in fact we can get from these we get a G-type gauge theory. Now, we can also get as PN and other groups, and I will not discuss this. There are other generalizations of that are relatively simple to study. But that's basically the bare bones aspects of how you do the geometric engineering of such gauge series. So the key is, if you basically look back at what I explained here, what you get is you have these spheres that fiber, and as you go to a particular point in this parameter space, this scalar moduli space, they can collapse, and that's where the gauge theory becomes non-abelian. So generically, it's an abelian gauge theory if these S are just, they don't have any degenerations. And special loci, they collapse, and you actually get G-type gauge theories. The key is also that the curves that actually collapse here have these types of properties, and these curves are really what's called -2, 0 curves. So what all of this is saying is the normal bundle of these curves is -2 degree, 0. So that's the non-abelian gauge theory part. Now, how do we get the matter hypermultiplets? That's the other ingredient for the 5D gauge series. So we have, again, so these come from now, so compact surfaces S, where the ruling, right, is by a reducible collection. So by reducible is actually collections, by reducible curve F. So F is some sum over Fi, and so we have F fibers S over some sigma, but now we also want that in fact F squared or the Fi squared actually are -1. So these are actually what's called -1 curves. So the way this usually happens is that at certain points where you have these vibrations, so actually there's a nice way of depicting this where you have sort of a collection of these surfaces, S1, S2, and so on. These are the gluing curves, so this is basically the curve sigma between these two surfaces. And now some of these have these vibrations, and then some of these fibers can actually become, so each one of these is a P1 fiber, and then for example here one of these P1 fibers becomes reducible. So it's a sum of two P1s that have a particular intersection pattern. Okay, and how do I then read off, given if this is sort of a hypermultiplet, then how do I read off the weight? So the representation is given by just now intersecting all the gauge divisors, the SI, with that curve Fi. So J. This is the corresponds to the weight the jth weight of this fiber curve. I find, why is this jumping around? So this is the weight under the carton associated under Sj, which is a carton of the gauge group, right? And so you intersect that with that curve, and it gives you that jth component of the weight. So that's how, from the geometry, we read off all these the gauge and the matter sector. But then also we would like to read off the prepotential. And the prepotential is in fact completely sort of, again, geometrically encoded in terms of 6CIJK. So phi I, phi j, phi k are just the Coulomb-Brown scalars, and the prepotential is just given in terms of, again, a complete geometric data. So this is on the Coulomb branch as opposed to extended Coulomb branch to start with. So that's just the intersection of all these compact divisors. So we take the triple intersection, that gives us a number, and that's basically then summed against these phi i's. And we can also get on the extended Coulomb branch, we can include non-compact divisors. So in fact, compactness, for compact divisors, the volume of these is proportional to 1/g². So as we take this to 0, we go to strong coupling. So this is going to the UV fixed point. So in fact, the non-compact divisors right, we take the volume of these d to infinity, and that means they're just, we've turned off the associated gauge coupling. So these are really flavor symmetries, right? So you can again think of this like what we did in the case of these box graphs, right? We're weakly gauging some of these. You know, you can think of bringing in these divisors and then decompactifying them again. Okay, so that's the dictionary. So this is sort of the abstract setup. What I want to do now is actually look at examples and also see how far we can go with various sets of tools that we have in algebraic geometry to study such things. Okay, so one thing I forgot. So the non-compact divisor, we can get, of course, the full F, phi, and MF from just looking at intersection, where we include in these CI, JK, also intersections with the non-compact ones. So actually, I will discuss an example shortly. Okay, so yeah, let's see what kind of examples we could consider. And here really the question becomes, what sort of geometry do you know and are you familiar with? And there are many frameworks for studying non-compact Calabi-Yau threefolds with canonical singularities. So probably the most familiar one is the toric Calabi-Yau 3. And they're nice because they talk to the dual to brainwebs. And they're very relatively simple combinatorially. But they have somewhat limited scope. So when I told you one of the motivations for studying these higher dimensional CFTs is indeed that many of them arise by compactifying from 60, and then they give rise to new CFTs or a lot of CFTs as you go down to lower dimensions. There's, of course, the way of starting with the realization of the 60 theories and then using that geometric realization in M theory and constructing geometries for 5D SCFTs. So using sort of what you might call F-theory methods to, so what this means in plain English is, i.e. elliptic models and so this is motivated by the 60 classification. There's also the way of just basically saying forget about the Calabi-Yau, right? In the end, if you're only interested in the SCFTs and you only want to really know what happens to various collections of surfaces as they collapse and have various degeneration limits, you can also just try to do a bottom-up construction of the surfaces, right? You can also model collections of surfaces that have a collapsing limit. Yeah, so you just take various surfaces. So in fact, the ones that are relevant here for Calabi-Yau threefolds, these are what's called either Del-Pezzo N surfaces or Hirzebruch surfaces. And blow-ups of these. So blow-ups in that case means just blowing up further P1s on these geometries. And then we could construct examples or just basically so this gluing together surfaces. That doesn't construct for you the geometry, but it certainly gives you a large class of CFTs in this way. And in fact, I think this is probably at the moment, our understanding of the models is as comprehensive here as it is here. So although these two approaches, right, these are actually very general and have sort of, how do you say, most comprehensive, they are not the most comprehensive in the sense of being accessible to people who haven't worked with this. So actually what I will do is I'll start discussing at least some of these aspects in the context of toric models and also show you a little bit the limitations of these toric models. And then tomorrow we will head to doing some more advanced algebraic geometric computations to see how we can extend that sort of diffuse the general reluctance perhaps to study elliptic vibrations. Okay, so let's start with an easy sort of set of examples. So in fact, sort of let's start with some toric models. And I think that might be useful because you might be most familiar with that framework. That could also be wrong, but that's sort of the assumption I was making. So toric models for threefolds, they're essentially given by a toric fan. Sorry, the toric, that's X, and so we actually have sigma is the toric cone, and it sits inside Z3. And it's generated by some vectors Vi over Z. And we want these Vi to, in fact, form a convex rational polyhedral cone. So Vi form So in sort of concrete terms, the way we'll think about these VIs is they have a common origin, and they're just some vectors, lattice vectors going out into Z3. So there's a 3D picture. And the map, the dictionary here is that the divisors are the rays. So they're generated by these vectors VI. Right? So this is V1, V2, V3. The curves, they correspond to two-dimensional cones. So generated by VI, Vj. And points, or so to speak, so the curves here we should really think of as di dot dj, and this is di. So the points, which are just di dot dj dot dk, they're just the sort of 3D subcones. So. And there are relations on these. So in fact, the plus linear relations that the sum of the VI di is 0 for the x coordinate, and there's a y coordinate 1, and the z coordinate 1. So there are 3 linear relations like this, and the canonical class, or minus kx, is given in terms of the sum of all these di's, and that of course for us has to be 0 for the Calabi-3 case. So in fact, this implies that all of these, the VIs, actually lie on a plane. So we can basically, without loss of generality, just say that they're just, let's say the z coordinate is just always equal to 1. So this is sort of, and we can use SL3Z acting on this full lattice to always arrange it to be that. So let's make an example. So the simplest examples, and so I have this grid paper here, is this here. Actually, I put the origin here. So 0, actually, let me make this slightly larger. You can see what I'm drawing here. So 0, 0. Then we have 1, 0, 0, 1. Oops. So these are the points. So we have 4 vectors VI. They all lie in this plane, right? So this is, say, V1, V2, V3, V4. So those are our 4 vectors that comprise sigma. And we have the linear relations. So the linear relations basically just tell us here that the divisors, so each one of these is associated to a divisor. So the di are the divisors associated to the VIs. And in fact, from here, we read off very simply that the one for V1 and V3, they're not independent. In fact, D1 is D3, and also D2 is D4. And also, in fact, you see there is in one internal point. So in fact, right, my lattice is, if I put some internal lines here as well, so in fact, there's one internal point. So there's in fact one vertex. So there's in fact the internal vertices. These correspond to the compact divisors. And the external vertices are the non-compact divisors. what we would like to also know is how many of these in general we have in terms of the various classes of curves and so on and so forth. So some of the abstract geometric data, which I think if you know Toric geometry, you know those anyway, but let me just summarize this here. So some topological, so H11 of these surfaces. So we'd like to actually know what these surfaces are, is actually the number of the neighboring vertices minus 2, right? So here, this is an internal, so these are compact minus 2. And in fact, one other thing we'd like to know is what is S cubed? And S cubed is just 10 minus H11 of S. Okay, and finally, if we have a non-compact, an intersection of a non-compact divisor squared dotted with associated to a vector V in sigma dotted with S, then we actually get this is sort of a curve, right? So we can think of this as we have some edge. So here's S, and this continues, and here's dV. Then there's a curve here, let's call that C. This is just the self-intersection number of C inside S. And so what we want, right, from our geometric engineering data is what's actually the self-intersection number of this curve, because that determines for us what are the characteristics in terms of the 5D SCFT. So if I actually want to determine the C squared, so let's call this C squared. So C squared, in fact, we can read off also from this toric diagram. So C squared times the vector V plus V, where basically we have, if this is our vector, so this is a terrible picture. So we have, say if this here is V, and these are the two neighboring vectors, V1, V2. So Vi are neighboring to V. Then C squared, that number C squared is determined by what is the linear combination such that when I add these together, I in fact get 0. Right, so in this case, for example, right, I have V1 plus V2 is V, so C squared needs to be minus 1. Okay, so that's essentially what this is. And of course, one other thing to note is in these toric diagrams, if I, in fact, so if we go back to this diagram here, this is in fact just P1 times P1 or F0, vertical surface. In this case, right, I actually, if I just draw this diagram here, I have just a singular, there's one divisor. In fact, this geometry on its own, I shouldn't call it like this. This is actually a singular geometry. In fact, only once I actually start introducing internal lines here and insert the curves, do I actually get a smooth geometry. So this is the singular geometry, and there's one internal vertex. And I can now introduce internal lines or curves. So partial desingularization means I now introduce into this diagram let me actually put this down here. So partial desingularization is if I now take this and I introduce, for example, one curve here. Now we learned that in fact, this one here, this divisor and this divisor are actually the same. So I can't just introduce half a line, I actually need to introduce a full line here. So this is a partial desingularization. This basically means I've introduced, so we've blown up, in fact, a rational curve of P1, but this still is a singular geometry. And the fully resolved one is where I essentially have a fully finely triangulated toric diagram. And in this case, there's basically no choice. So that's a slightly degenerate case where this resolution is essentially unique. So this is not a fully resolved. Okay, so in fact, for this particular example, we can now work out what actually are the various curves. So for example, one conjecture would be that this partial resolution, this corresponds to some non-abelian gauge theory. And since there's one compact divisor, this probably is a rank 1 theory. So we should check out what exactly the geometry of this is. So that's something we can just analyze with the fully resolved model, determine all the intersection numbers, and then see what this partial resolution corresponds to. So let me actually introduce just a bit more notation. So we had V1, V2, V3, V4, and then let's say these are curves C1 and C2. They're just two curves because V1 and V3 and V2 and V4, the associated divisor are the same by linear relations. H11 is 2, and S cubed is 10 minus 2 is 8. And then the curve C1 is just the intersection, if this is S, and I should probably, just so I don't confuse you here, just call these here D. So D1, D2, D3, D4. And remember the relation that D1 is D3 and D2 is D4. So we have C1 is the intersection between S and D1. And C2 is the intersection between D2 and S. And now we can compute the intersection numbers. So in fact, from this rule that I produced up there, so D1 squared dot S is in fact 0. D1 dot S squared is minus 2. And D2 squared S is 0. And D2 S squared is minus 2. So in fact, if we just introduced C2, so this would be C2. C2 is what we called earlier minus 2, 0 curve, right? So it has exactly this property, right? You should think of this as, now this is C2 dotted with S, yeah? So that's exactly minus 2, 0 curve. So if I just introduce this curve C2, this actually would correspond to saying that curve is the collapsed version of this divisor S, where it collapsed the ruling. And so this is sort of the curve C2 in the partial resolution is a ruling. Yeah, and then we collapsed C1. And so we get here, in fact, from the intersection numbers of S cubed and so on, this is in fact an SU2 or an A1 singularity. And we can now also compute, of course, the triple intersection number. So the prepotential for this geometric theory, right, we said is 1/6 S cubed, phi cubed, and that's 8/6 phi cubed, which is 4/3 phi cubed. And that's, if you now go back to the geometric one, this is just the same as the one for an SU2 theory. So compare with the prepotential for SU2 and the flavors from lecture 1. And you'll find that, in fact, this corresponds to exactly an SU2 0 theory. So NF is 0. And also there's no theta angle. So that's nice. So we found, right, if this dictionary, I didn't prove to you a dictionary that this is really giving you the series, but the pre-potential matches, and that's a good indication that that theory is in fact, this geometry is modeling something related to this theory. What you've also seen is that the structure of the rulings, right, so finding some kind of partial resolution where you have essentially these curves, right? So in this case, it's a very symmetric situation, so you could collapse it also along C1, along C2, keeping C1 at finite volume. Basically what you can now sort of see is finding rulings is sort of one way of mapping it then to some interesting non-abelian gauge theory description. So,
excuse me.
Yeah.
Just as one question, can you also reproduce the quadratic term, so the gauge coupling term from this geometric part?
The which term? The
gauge coupling, so the quadratic term in phi.
Yeah, so you could also, yes, so for this, you basically, so here I've sort of done this in the fully resolved geometry, right? So now the gauge coupling term, right, is also, it's like a mass term as well.
Right.
So you can also think of this in terms of coming, right, if I now include all the non-compact divisors as well. So I don't just look at S cubed, but also intersections of compact and non-compact ones. I can reproduce also the sort of the more extended Coulomb branch part of the, and I will explain this hopefully. So I won't do it in these toric examples because in fact you don't see the full structure of the non-compact divisors always in these toric examples, but you can, I will get there hopefully tomorrow.
Okay, thanks.
So one thing that of course we like to know is these toric models with SU2 with no flavors, that's nice. And the problem with this is of course the toric models, and models. And in fact, a nice place where you can read this is this paper by Cyril Closet, Del Sotto. Oops. And if you're actually really interested in how the toric also talks to the 2A description, if this is your thing, then that's certainly the place to read that up on. These are rather limited. So in fact, there are more toric polytopes that we can write down, but it's limited to NF equal to 0, 1, 2, and you also can, in NF equals to 0, you can also get these SU2, 0, and pi versions, but that's about it. So in fact, the toric models, and I will write them down here, and I would sort of encourage you to try to see whether you can extract from it, as we did in this SU2 0 example, all the field theory data. So let me just sort of draw these out for you here, and then you can try to construct them yourselves. So they always have one internal vertex. This is the theory, which is SU2 with 2 flavors. From there, we can essentially go to one other model, which is sort of taking the following geometry here. So in fact, this is maybe a good point to explain what these transitions are between these series. So here, this particular vertex here is actually what we call so this curve, if I had a curve here, let's put this curve in. So this divisor, the curve that connects now the compact divisor with this non-compact divisor here, this is actually what's called a -1 curve, right? Because just in terms of our rule, it's a linear combination of this one, these two neighboring ones. If I actually put the full triangulation in, this is the full triangulation. This is a -1 curve, so this curve C is C, so C squared is -1. So this corresponds to some hypermultiplet, fundamental hypermultiplet. Now, in geometry, a -1 curve can be flopped. So its normal bound is such that you can take its volume to 0. So you can take the volume of C to 0. So that's one of the instances where we can collapse the curve to 0 volume. And then there is, in fact, the topologically distinct resolution. So we can flop this and, in fact, flop it out of the surface, right? So this whole object here characterizes one compact surface, and all the curves that are contained in it are shown here. And now we can do a flop transition. So in fact, we can just take the same diagram and retriangulate. So the flop is like what you know from the conifold. You have a curve like this, like that. You can resolve, right? You have an equation, UV is WZ. You can either resolve with UW, or you can resolve distinctly with UZ, and those gives you two topologically distinct resolutions. And so one way of thinking about this geometry is there are all these mini conifolds contained in here, and we can just flop that curve just from here to here. Now, in the interpretation that we had in this sort of in this sort of M theory to 5D gauge theory interpretation, this isn't just a mundane operation. In fact, if you now look at this curve that we've obtained here after the flop, that curve doesn't intersect the divisor S. So let's call this C prime. Right, so C prime dot S is in fact 0. It doesn't connect into S. So what used to be a curve that was hypermultiplet matter, it was charged under S. So C dot S is non-trivial, so just 1 or something for fundamental weight. Now that curve actually, once you do that flop transition, the curve isn't charged under this SU2 carton, and so is uncharged. And so what these flops can correspond to is, in fact, decoupling, right? So we started with some number of hypermultiplets. So my claim was this is SU2 with 2 flavors, and it's an exercise I would like you to do in your private time, now following what I explained to you today. In this case, the flop actually is a decoupling of that particular hypermultiplet matter. And there are also flops that are much more mundane, and they just correspond to sort of different Coulomb branch phases. And so they're just different gauge theory phases that do not have an interpretation like a decoupling. And that's something we've actually seen in our gauge theory analysis. So what I'm doing at the moment smells very much like this story I was telling you last time about these box graphs and Coulomb branch phases, where you have certain operations on a given Coulomb branch phase, in this case a fully resolved geometry, and doing these types of transitions or changing the Coulomb branch phase can have the interpretation of a decoupling. So in this case, indeed, this is the decoupling and the diagram. So this theory, in fact, you can think of now as SU2 with 1 flavor. And in fact, strictly speaking, right, this vertex here is now not talking to the rest anymore. So you can think of it as there's still the C prime is still sort of, more speaking, a curve there, but the diagram that really characterizes the SU2 with one flavor is the diagram that's just this here, this toric diagram. And this is now the fully resolved case here. And now we can continue this, right? So this is, once you take then the mass to infinity, right? That's the toric diagram for the theory. And at that point, there are now two choices. So if I just copy this over, if we continue this, here, from this diagram, you now have, essentially, if you look what kind of curves you have, there are two -1 curves. In fact, this is, why did I draw it with this? Someone should have stopped me here. There should be this, should not be a change. It's preempting what I was going to do. Because that was already the phase where it's decoupled. Anyway, so essentially the two inequivalent -1 curves, this one here and this one here. And we can do the flops and they give us two different diagrams. So the flops just mean we flip this curve over, and then what we get is the diagram, which is this one here that we had. Or if we take the one down here, we get a slightly different diagram, and that's the following. And so this is SU2 0, and this is SU2 pi. And in fact, in this case, there's still one -1 curve left, which is this one, right? So the sum of these two is minus that. And if we flop that, we get to the diagram like this. And that's actually the geometry of a P2. And now this is special in the sense that you actually do not, so all of the ones so far, they have a nice ruling. It's actually the ruling, let's put that in some color. So the ruling, we can always put in a ruling in some particular way. For example, here, right? So these are all curves, and I can collapse the other, I can remove all the other curves and I get an SU2 singularity. This does not have a ruling. So if it doesn't have a ruling, but it can still be, right? So there's no way you can take a P2 and write it as a fibration of a P1 over another curve. But you can still collapse the P2. So in this case, there's no ruling, but the P2 can be collapsed, right? So there's still an SCFT at the origin of this relative Kähler cone. With a Coulomb branch, extended Coulomb branch. But so these are what we would call non-Lagrangian 5D series SCFTs. Right? There's no non-Abelian gauge theory that underlies it. There's a Coulomb branch description in terms of U1, but there's no intermediate SU2 gauge description, whereas for all the other ones there is. So we've gone from SU2 with two flavors to SU2 with one flavor. Then the SU2s with no flavors with theta angle 0 and pi, and then to P2. And that's essentially what the toric geometry allows you to model in terms of, the SU2 Coulomb branch phases. So in fact, you see there's no choice in each of these triangulations of this toric diagram, there's no choice. So that sort of indicates that there's just one phase. And that's precisely the kinds of phases that we had here, right? So in fact, what we reconstructed is sort of a sub-diagram of this, which is this. Yeah. And the gate series phase, of course, for SU2 with NF flavors will not model the SU2, the P2 theory. So that's why we don't see that. But that's basically what we've now realized in this toric geometry. It's of course very disappointing because in fact, what you see from here is there's not really too much we can extract above. So none of these models above are actually toric models. That sort of exemplifies the limitations of this toric approach. But it's certainly something that probably you've seen before, and so you can somewhat relate to more than what I would do next time. So let's see how we're doing in time. Okay, so we're basically out of time. I just wanted to sort of ask you to look at, like last time, I want to look at one example and to give you a little bit of sort of a way to do a work on, let's say, some concrete examples. So what I just said is not entirely true because there is a way of realizing. So these are particular toric diagrams. They're sort of isolated. They don't have any. So what you see here is basically these strictly convex toric diagrams. So what I want you to look at is the following diagram and determine for me until tomorrow. Actually, let me again double the size of the grid. So actually, which one did I want you to do? Yeah. So this is the toric diagram. This is not strictly convex, right? So this is so strictly convex, meaning there are no vertices on the edges. Here there are vertices on the edges, but I would like you to now look at this. So again, there's one internal vertex. So I will give you the one of the fully triangulated diagrams. This is an example triangulation. And I would like you to determine what is the theory. And what you will see is, in fact, now there are non-compact. So there's one, it's rank 1, because there's one internal vertex, right? But now there are lots of external vertices. And so using these rules of, how we can read off the matter, how we can read off flavor symmetry from non-compact divisors, I want you to sort of study this particular model. This is the so-called T3 model. And that's sort of one way within the realm of torics, you can actually get to something that's beyond these low SU2 ones. So it's a slightly different construction, but these because we now allow for these non-compact divisors that are giving sort of explicitly the flavor symmetry, I would like you to study that in this context. Also here, note the triangulations is not unique, right? In this case, so for example, actually this is probably in general, right? So in fact, you could could generalize this. Another example to consider is this T4 model. And these are just good ways of exercising these toric methods. Okay. So once you go to this model here, these triangulations, this is now higher rank theory, and I also, so this is T4, and I would like you to sort of, again, look at the possible triangulations that you can have here, and then also the structure of how the decoupling works. So in decoupling we discussed is flop transitions, so like we've done in this example here. So for example, here we have these three internal verses, this is a rank 3 theory. Now, what kind of gate theory description could there exist? So what kind of rulings are there? And then also, how do I decouple hypermultiplet matter? Where is the hypermultiplet matter? And then how do I actually decouple that consecutively? And I'll discuss that tomorrow at the beginning. But then all of these methods, these toric methods, are quite limited to particular instances. And I want to sort of provide you with a more general framework, how to study theories. Say all the 60 theories, compactify them, and then study the 5D avatars of them. And that requires a little bit more sort of direct algebraic geometric methods. Okay, so there was only one question today. Do we have any other questions, any discussions, anything that I should perhaps highlight a bit more?
So far, nothing in the chat, but I have a question.
Marcos actually has a question. Okay, yes, go ahead, Mauricio. Yes,
Marcos,
go ahead.
okay.
No, go ahead, Mauricio.
Yeah, so my question is, so far you have talked about resolution of singularities by blow-ups.
Yeah.
But you can also resolve singularities by the formation of complex.
That's right. So in fact, that is lecture 4 when we discuss the Higgs branch, right? So, so I know yesterday probably because it was different here. So in fact, right, so we have from X, right, indeed, we can resolve, and that's really the Coulomb branch or extended Coulomb branch. But you can also deform. And that actually is something that depends a bit more on. So at the moment, we don't have a very good understanding of how this works in general. So this works for isolated hypersurfaces and also perhaps complete intersections. So Xi and Yao have also studied these types of geometries, and I think there were other papers with a subset being Xi and Yao on the complete intersections. Studying the deformations is harder because, right, it's not just a classical problem. There are quantum corrections. So by deforming the singularity, you're introducing compact 3 cycles. And so you can get M2 instantons that will correct this, this metric. Yeah. So that's why that's a slightly more harder problem. Still, there are these other methods where also Marcos is one of the experts and that were developed. In fact, that's why I wanted to also discuss the torics, because there's some brainwave motivated methods to understand the Higgs branch. So this is the Higgs branch, yeah, but only sort of the classical part of the Higgs branch. So this requires some additional input. But yeah, that's certainly something we will hopefully get to in lecture 4. Lecture 2 and lecture 3 is the resolution story.
I wanted to ask about the SU2 with theta angle 0 and pi. So if you just look at the geometry and compute the prepotential from the intersection numbers, is there any way of telling that the theta angle from the geometry?
Yeah, so no, so that's a tricky one, yes. Right, so I think there's sort of always the question, how do you actually tell from the geometry that how do you compute the theta angle? I think this, I don't know.
Yeah, but at least you can distinguish whether
you
the
can
geometry from geometry.
Yeah, so that's right. So basically they're distinguished, right? Indeed, as Hicho was saying, these are the two completed. So one thing you can do, okay, so here's maybe one thing. When you have theta equals to 0, or in fact Chern-Simons level 0, there can be certain symmetries. So we'll discuss something called CFDs, and when these have certain Z2 symmetries, then the Chern-Simons levels or the theta angles are probably 0. This is sort of a rule of thumb, but it's not something where I could just, take M theory on this thing and boom, and here is theta is pi. But you can certainly distinguish the two.
Sure. Okay.
Now maybe Hicho, you want to add something to this, but I think that's sort of how far one can go with the theta angle.
Thanks.
So one other thing I wanted to actually really, so of course time is always short, but when we were doing all these Coulomb branch phases, right? This sort of thing, but also in the first lecture here. Okay, so this is what we did last time. These Coulomb branch phase, these sort of things. These processes, right, going from these design assignments and then doing these transitions, you see that in the toric diagrams, it's actually these flops that you can do. There's a very nice sort of correspondence between many of these flops and these Coulomb branch phase changes. So one of the examples I think that's useful to consider in this context is this T4 example, which is actually quiver gauge theory, and to construct the Coulomb branch phase sort of the box graphs and then really map this to specific toric triangulations, right? The nice thing about toric geometry is really all the triangulations are completely just putting in, different flipping sort of curves. And so you can really nicely see how the different phases, the gauge phases map to the Coulomb branch phases, the toric phases map to the Coulomb branch phases. But again, there are limitations because indeed this toric approach is not the most general that there is. Are there any questions from students? So I had questions from faculty and comments from faculty, but I'm a bit worried about the students. I'm not hearing any questions. It's usually not a good sign. So do you want to perhaps tell me? So one thing actually I would like to know is, I should probably ask this after lecture. One is how much geometry everyone knows. I basically assumed that you know toric geometry, and I sort of buzzed through that pretty quickly. Probably you don't know too much other sort of more general algebraic geometry tools, how to resolve the singularities. So I will go through that in more detail, but it would be nice to have some feedback from the students on this.
You can make a poll. I don't know how.
Oh, we could make a poll. So, yeah, but what would be the question? We ask the poll. So is it too simple? Okay.
No, sorry. So let me know the question. I can edit the poll very quickly.
Can we
level of algebraic geometry from
so yes, are you
0, 1
okay,
to
so what's your level of algebraic geometry knowledge? Is it sort of
what's your level of
knowledge in algebraic geometry? And let's say that levels of
like 1 to 3
imagine
or 1 to 5 or
1 to 5, and well, 5 being I'm an expert, and 1 is I barely know what P1 is.
I will mark 2. I will mark 2 for myself.
I think we're all going to mark.
Barely know what P1
No,
is.
don't write it. It's just this was just to
Okay.
fix it for everyone. Let's put from 1 to 5.
I just
From 1 to 5, and then I was just sort of setting the scene. 5 is like, you know, I'm Dave Morrison, and 1 is I'm actually just learning how to understand what actually the basic concepts are.
I think that makes us all 1.
okay.
Yeah, 5 is like super high.
I don't think that's true for you, Peter, but I think I would, yes, that would be useful to know, because that depends on how much detail I will provide tomorrow in the more, this was toric geometry, but I'm asking sort of really algebraic, you know, when you do certain computations in algebraic geometry, like doing a resolution algebraic geometry, intersection calculations, that sort of thing.
Sorry, I cannot.
You cannot do it. So I can still see a poll there.
Oh, I need to stop this, I think.
I think you might need to stop the other poll first.
Yeah, what's
the first poll was, is it simple, yes or no?
Level of.
Which also is a useful thing to ask, but. But in the meantime, do students have questions? I mean, so about these toric models, the toric models are basically sort of a nice playing ground where one can learn a lot of the things quite explicitly, work out everything. Are there some questions about how I see certain characteristics of the theories?
Yeah, actually, can I ask a question?
Sure, go ahead.
So,
yes.
Can you distinguish the theta angles by higher form symmetries?
Yes, so you can. Indeed, so the higher form symmetry, you can calculate, so I will hopefully get to that. So indeed, you can, so one way to distinguish the theta equals to 0 and pi cases is by looking at the one form symmetry. So the one form symmetry is sort of like this. We have 0 form symmetries, that's a flavor symmetry. So the charged objects are point-like, and the charge operators are codimension. One form symmetries, the charged guys are the line operators, and we can calculate the higher form, the one form symmetry in terms of you know, essentially completely geometric methods too. So morally speaking, it's the non-compact curves, right? So these are these Wilson lines, infinitely heavy, modulo screening, so compact 2 cycles. So in the geometry, these are like non-compact 2 cycles, which are basically the world lines of, you know, particles, very heavy particles, modulo screening, compact 2 cycles. And this is something we discussed in a paper with Dave Morrison and Brian Willett. And in fact, for the toric models, one just needs to take what's called the Smith normal form. Right, so generally, you need to calculate the non-compact cycles and take this relative homology. But for the toric models, it's very simple. Take the Smith normal form of these vectors vi. the matrix of these vectors vi, and that gives you, so the Smith normal form gives you a diagonal matrix with integer entries, and from there you could read this off. And in fact, for the SU2 0 case, that's a Z2, and for SU2 pi, it's empty. So the one form symmetry. Yeah, that's one way you could.
I see.
Yeah, that's a good question. In fact, in this way, you can indirectly indeed calculate it. Yes.
Okay, thanks. Yeah.
Cool.
So for this one form method, you can just use the gauge theory to distinguish these two?
You mean for the one form symmetry, you can also in the gauge theory, of course, distinguish it. Because the center symmetry also gets, so this is basically the center symmetry of the SU2.
Yeah.
And the theta angle will break that. But so the way I understood the question by Duan is that the question, what could you calculate that from just a purely geometric framework? And indeed you can. So for the toric ones, is you just take the external vertices and compute the Smith normal form of that matrix.
Yeah, but to see the emptiness of this one form symmetry for SU2 as theta equal pi, I think we need to do some instanton calculus, right?
In the gauge theory, you mean?
In gauge theory,
yeah, absolutely, yes, yeah, I agree.
Okay.
Yeah.
Thank you.
I think this is also similar to you see a similar thing for SUN, and if you have transimus level K, then again, you've got the charged object, the K charged particles, right? You really need to do the full instanton calculus to see that, right? If I understand this correctly. So similarly here in the geometry, there will be charged particles that could screen that, and they could be coming from the instanton particles. In this case, this gamma 1 is G, C, D.